This is going to be the lecture video for Chapter 2 in your book, Atoms, Molecules, and Ions. There's a lot of information to cover, so let's just jump right into it. In the last chapter, we said that chemistry, in the most general sense, is the study of matter. Since matter is everything that has mass and takes up space, which is a super broad grouping, we can break it up along lots of different lines, but one of the most basic is pure substances versus mixtures, based on whether any given substance has constant properties and composition. We'll cover certain types of mixtures in more detail later on in this course, but in this chapter, we'll focus on pure substances. Pure substances can be further categorized as to whether they can be simplified chemically in some way. As we'll see later, this essentially boils down to whether it consists of more than one type of atom or not. Anything that can be simplified chemically, and hence that consists of more than one type of atom, is said to be a compound. Anything that can't is said to be an element. Interestingly enough, all naturally occurring matter consists of only about 94 distinct elements. We've since discovered a few more elements under exotic laboratory conditions, but with such a relatively limited set of elements comprising all matter, we have names and chemical symbols for all of them. The chemical symbol is a 1 or 2 letter abbreviation that is unique to each element. The first letter of a chemical symbol is always capitalized, and if there is a second letter, it's always lowercase. For the most part, chemical symbols are what you might expect as abbreviations based on names. Here we're looking at an alphabetized list of some of the more common elements, and you can see that they all have pretty sensible abbreviations based on their names. If we continue this list of common elements, you can see this pattern continues for a while, but then there's this list of 8 elements at the end where they have seemingly mismatched chemical symbols given their names. For the most part, this happens when the abbreviation comes from the original Latin name of the element, which I've provided in this chart for reference. Since all of these are common elements, you'll want to recognize these names and symbols. The chemical elements are arranged into a chart called the periodic table of the elements, or just the periodic table for short. A basic periodic table looks like this, with the elements arranged in order of increasing atomic number and placed into columns based on certain similarities between them. A couple of things about the periodic table while I'm introducing it. Every semester I teach, there's always at least 1 or 2 people that tell me that they've had to memorize the entire periodic table in middle or usually high school. Let me just say that even thinking about that makes me pretty angry. While you should know how to use certain aspects of the periodic table when provided with it, and it's quite helpful to recognize the names and symbols for some common elements, memorizing the whole thing is, at least at this level of chemistry, one of the most counterproductive and asinine things I can imagine. If you're one of those people that had to memorize the periodic table, I'm really sorry. Contact a lawyer because you may be entitled to financial compensation. In the context of the periodic table, the rows are called periods and the columns are referred to as groups. If you've seen the periodic table before and wondered why there's that block of elements separate at the bottom, there's actually nothing special about them particularly. I've shown you what the periodic table actually looks like without those elements cut out, and the table is not usually shown this way for the simple reason that it's really long and unwieldy like this. The periods are numbered 1 through 7, top to bottom, and the groups are typically numbered 1 to 18. In the non-elongated form of the table, these are numbered simply from left to right. The system your book uses is actually not the 1 to 18 system, but the 1A to 8A system. The main difference is that in the latter system, groups 13 through 18 are labeled 3A through 8A instead, where the number matches the last digit of the column in the 1 to 18 system. So group 13 corresponds to group 3A, group 14 corresponds to group 4A, etc. Besides periods and groups generally, there are various ways of dividing the periodic table into groupings of elements that share certain characteristics. One grouping that simply breaks the table up into regions is the classification of main group versus transition metals versus lanthanides and actinides, which was shown a couple of slides ago. The main group elements are all those in groups 1 to 2 and 13 through 18. The transition metals are in groups 3 through 12, and the lanthanides and actinides are the 2 rows below the rest of the table. Other ways of classifying elements that we'll look at do so along lines of similar chemical and physical properties. Let's briefly go into those terms. Properties are just another term for characteristics. Intensive properties are qualities of matter that don't depend on the amount of matter in a sample, and extensive properties are those that do. Among intensive properties, we can divide them along physical versus chemical lines. Physical properties are those that do not pertain to changes in a sample's chemical makeup, while chemical properties do pertain to such changes. Physical properties might be things like temperature, color, melting point, or many, many others. This list here isn't meant to be comprehensive at all. Chemical properties include things like the tendency of iron to rust, the flammability of gasoline, silver's propensity to tarnish over time, etc. These all pertain to the tendencies of these substances to undergo particular chemical reactions under certain conditions. Elements on the periodic table often belong to groups or columns based on their similarity to other elements in the same group or column. Let's look at a few particular such groups, starting with the alkali metals, which are the elements in group 1 with the notable exception of hydrogen, which is in group 1 but it's not an alkali metal. These elements, from top to bottom, they're lithium, sodium, potassium, rubidium, and cesium, are all, as the name suggests, metals. As metals, they all have reflective appearance and high electrical and thermal conductivity. Compared to many other metallic elements, however, they have some remarkable properties. First and most famously, they are extremely chemically reactive. In this slide, we see a piece of sodium metal reacting with water in a way that's typical for alkali metals, violently, and often with a resulting fire or even a small explosion. If you're thinking to yourself, that's not what it looks like when I add sodium to water, you're probably thinking of salt, and it's worth mentioning that the sodium, say in your diet, is in the form of these salt compounds like sodium chloride. This is sodium as a pure element uncombined with any other element. That's also why it's metallic looking and not in the form of white crystals like it would be if it was salt. Other properties of the alkali metals are that they are much softer and have much lower melting points than most other metals. Most of the alkali metals can be cut easily with a pair of scissors. I've done this before and it's really weird. They have almost the texture of butter, not anything like a typical chunk of metal. And the low melting points mean that you can heat these metals up, in a couple of cases around body temperature, and they become liquids. It's really weird stuff. Those are the group 1 metals, alkali metals. If we look at the group immediately to their right, group 2, we have the alkaline earth metals, beryllium, magnesium, calcium, strontium, and barium. And this includes all elements in the group, unlike the alkali metals where hydrogen wasn't a member of the group despite it also being in group 1. The alkaline earth metals are often described as being somewhat similar to the alkali metals, but less extreme. They have the usual appearance and high electrical conductivity of metals generally, and like the alkali metals, they tend to have high chemical reactivity, be relatively soft for metals, and they have relatively low melting points, although these properties are all less so than with the alkali metals. On this slide, you can see a representative example of this family, magnesium, exhibiting a high chemical reactivity, burning with bright white flames in the presence of oxygen in the air. But this reaction doesn't start spontaneously like the reaction of sodium with water. Magnesium, while still chemically reactive, needs to be heated to a high temperature for a reaction like this to occur. We looked at the first two groups of the periodic table in depth. Let's now take a look at the last two groups, starting with group 17 or 7a, the halogens. These are non-metallic elements, so they're very different than the alkali metals or alkaline earth metals. The members of this group include fluorine, chlorine, bromine, and iodine, or as it's sometimes pronounced, iodine. They have somewhat variable physical properties. Fluorine and chlorine are green or yellow gases. Bromine is an evil-looking dark red liquid, as you can see on this slide, and iodine is a dark brownish-purple solid. What they do share, though, are similar chemical properties. They're all highly chemically reactive, especially towards metals. Let's move on to the final group of elements that we'll discuss in detail for now, the noble gases in group 18 or 8a. Unlike the previous families of elements we've seen, these are extremely chemically unreactive. That's actually what noble means in noble gas. It's an old-fashioned term for unreactive. Most of these elements are not known to undergo any chemical reactions whatsoever, helium, neon, and argon being those. A few other noble gases, krypton, xenon, and radon, are actually known to be able to react with a small number of other elements, but only under pretty extreme conditions. The other part of this family's name, gases, tells us their main physical property that they have in common. They're all clear, colorless, odorless gases at room temperature. The unreactivity of these elements means they're fairly boring from a chemical reaction perspective, but one interesting niche use of them is in signs like the one shown here. In fact, these types of signs are often called neon signs, since that element was the first one used for these purposes. But all of these noble gases glow brightly when placed in a tube and exposed to a high voltage, hence the use in these signs. Helium glows a pink-orange color, neon, as you may know, glows a bright orange color, argon has a purple glow, krypton is kind of whitish purple when it glows, and xenon is bluish white. So those were a few specific groupings of common elements. Let's look at a fundamental grouping that we can apply to all of the elements in the periodic table, metals versus nonmetals. Metals, as shown here, are most of the elements in the periodic table. They include all transition metals, lanthanides and actinides, and they also include many of the main group elements as well. They're concentrated towards the left and center of the periodic table, with the exception of hydrogen, which is a nonmetal, but it's in the leftmost column of the periodic table. Metals tend to have shiny appearances. Most are silvery, although metals like copper and gold are exceptions to that. Most are good electrical and thermal conductors, and almost all of them are solids at or near room temperature. The one element that is a metal, but not a solid at room temperature, mercury, is a silvery liquid. Metals also have certain chemical properties in common with each other, but we'll get more into that later. Most of the elements in the periodic table that are towards the upper right portion of the table are nonmetals, and we already saw two families of nonmetallic elements, those being the halogens and the noble gases. The properties of nonmetals are somewhat variable, but largely are opposite to those of metals. Some are solids. One of them, bromine, is a liquid, and quite a few of them, including all the noble gases, are gases. They are generally poor conductors of heat and electricity, and their chemical reactivity, except for the noble gases, is opposite to that of metals. Finally, we have a handful of elements along a staircase-shaped boundary between the metals and the nonmetals that are called semi-metals, or metalloids. These have properties that are intermediate between those of metals and nonmetals, both chemically and physically. Notably, on the physical side of things, they're all solids with an intermediate ability to conduct electricity called semiconductors. Many of these elements' practical uses are dictated by this one property, which is why, for example, silicon, a semi-metal, is used so much in computers.